Thank you very much, Joaquin, for having me. It's a pleasure to be here and to talk about my work on predicting medical complications. So maybe as we are a bit ahead of schedule, I'll explain you what I'll try to do today. So the first 2/3 of my talk are about our attempt to predict sepsis in intensive care units using machine learning. And then if time permits, the last 1/3, because I know this is also very dear to the CAMDA community, I also have slides on our project to predict antimicrobial resistance from mass spectra. So if time allows, I'll also cover this last third. If not, then I'll focus on sepsis exclusively. So the talk is, as Joaquin mentioned, maybe not such a typical talk for me, because as Joaquin said, I'm coming originally from more theoretical algorithmic machine learning, but today I will focus on the aspects that are important for CAMDA, namely the critical assessment of massive data analysis and all the pitfalls that you encounter when analyzing medical records and clinical data and trying to use them for predicting complications. In this spirit, I will highlight a few problems and a few challenges that we have to face and ultimately solve in this field in order to really bring this idea of using machine learning for predicting medical complications to a success. Now, first of all, the idea to predict medical or clinical phenotypes is not new. This is a research topic that has been studied for decades, and you'll find a lot of papers on that in the literature. Now, what is these days different maybe from the past is that we have more data than ever available for this task. We have more computing power available to solve to compute more complex models on this data. So this brings us into a new situation. Still, what is extremely important in this field is, of course, is true probably for all of machine learning and the life sciences, is you really have to carefully choose and motivate why the prediction problem that you are solving is actually relevant for the clinic. And that's why I will start by explaining why there is actually a clinical need for sepsis prediction. It's not just an academic exercise that you could do it. Why is this clinically relevant? In order to answer that question, let's first of all remind ourselves what sepsis is. So it's a syndrome with 47 to 50 million cases per year, and at least 11 million of those died. So that means there's one death from sepsis every 2.8 seconds. And even one in every 5 deaths worldwide is associated with sepsis, and it's the major cause of mortality in intensive care units around the world. So sepsis is really a fundamental health crisis. You may know that even often in those patients that died from COVID-19, like the ultimate cause of death often also was sepsis. So it's often the final step from a bad infection to death is often accompanied by sepsis. Now, what is now sepsis? I called it a syndrome. Sepsis, in these infographics from the World Sepsis Day, is described a bit more informally as arising when the body's response to an infection injures its own tissues and organs. So there are important elements in there in this sentence which also occur in the official sepsis 3 definition of sepsis. So this is the international consensus definition at the moment. So sepsis is a dysregulated host response to an infection that starts hurting the patient, him or herself. So it's becoming a life-threatening organ dysfunction. And this is summarized in this international consensus definition as sepsis is a life-threatening organ dysfunction caused by a dysregulated host response to infection. So these 3 components are really important: the organ damage, the infection, and the dysregulated host response to this infection. Now, can you diagnose, can you predict sepsis? There are a few symptoms that might indicate sepsis. like slurred speech, extreme shivering, passing no urine, and severe breathlessness. These are all, as we would call them in machine learning, weak predictors of sepsis, but none of them is giving a strong or exact predictor of sepsis or diagnosis of sepsis. So all of them show a weak correlation to developing sepsis, but they are not a strong predictor in the machine learning sense. Still, it would be very important to have such a strong predictor because every hour of delayed effective antibiotic treatment increases mortality. So when you know there's an infection that may lead to sepsis, there is a way to treat it, namely you should identify the pathogen and then give an antibiotic to the patient that is tailored to that pathogen. But another pitfall and another problem here is that the bacterial species identification in blood, that's the typical thing that you do then in such a case, still takes between 24 and 48 hours before you know which pathogen it is and before you know which antibiotic to use in this particular case. And the longer this whole process takes of identifying the bacterial species, of choosing the right antibiotic, the further the mortality goes up in the intensive care unit. And this now leads to our motivation, the desired motivation that I described or hoped for before. Namely, the motivation is that detecting and treating sepsis earlier will allow the treating doctor to earlier intervene and to give the right antibiotics to a particular patient. And therefore, detecting and treating sepsis early is of highest clinical interest. There's a very interesting and very fitting statement by Niccolo Machiavelli from Il Principe, where he describes the principle that we are following here for a related syndrome, hectic fever, not exactly sepsis, but related. And he says that hectic fever at its inception is difficult to recognize, but easy to treat. Left unattended, it becomes easy to recognize and difficult to treat. The same holds exactly for sepsis. And now the task for machine learning is to recognize sepsis at an early stage where it is still easy to treat. This is the hope that we have in this work. Now, how have we and others in the field tackled this problem? I'll describe it by first formulating what we use as input and what we use as output. So what we use as input, we and others, is intensive care data on a patient. So you know, and you can see it here on the right, that a lot of data is being collected on an ICU patient. Like vital signs are being collected, lab tests, you have typically access to the health history of that person, you record which drugs are being given to this patient. So all of these types of data are the input to our machine learning algorithm. Often, so time series with very high resolution. And then based on this data, based on these potentially high-dimensional time series, we then try to predict sepsis-related phenotypes, like the onset of sepsis, septic shock, which is a severe form of sepsis, or even ultimately mortality, like will the person die from sepsis. So this is the overarching principle. We put in the ICU data describing a patient up until time point t, and then we predict whether one of these sepsis-related phenotypes or events, you could also call them, will happen in the future, so typically within a certain time window of X hours. And my own lab has tackled this problem from two perspectives, and namely using association mapping in time series and using classification of time series. So the first one, this association mapping, was actually the topic of contributions of ours to ISMB over the last 5 years, to ISMB and ECCB. So the idea here is similar to what is called genome-wide association studies in genetics. So there, one is looking for single nucleotide polymorphism, so genetic variants that are associated with a phenotype. In the same spirit, we are here looking for subsections, segments of time series, so trajectories, you could call them, or even in more data mining terminology, you could call them shapelets, so particular shapes in these time series that are associated with developing sepsis. And we have developed techniques for this over the last 5 years, so finding time series fragments, time series shapelets that are associated with sepsis. So I will not talk about this today. I'll talk about the second type that is actually also more predominant in the literature, namely treating this as a classification problem. And that's very close to what I described before, namely, you take all the data that you have on a patient up until time point T, and then you consider this a classification problem, namely to predict, will this person develop sepsis in the next X hours, yes or no? This is the classification problem we are trying to solve, and this has until now, actually these days, been one approach that we are taking in my lab. It's also the predominant one in the literature. In fact, even years before we started working on this, there had been papers on exactly that task, like predicting whether someone will develop sepsis from intensive care records. And at the time we started, there were about 20 papers, and it was, after reading them, we came to the conclusion it's very hard to compare them. It's very hard to do a critical analysis of massive data analysis, so a CAMDA, for this particular topic. So the first big thing that we did in this domain was to do a systematic review of this literature to find out how we can compare these different approaches that have been developed for sepsis prediction. And to even answer the question whether we can compare them at all, and whether there are common challenges and pitfalls in this literature. And we identified a lot, but you'll see this in a minute. So this was spearheaded by Michael Moore and Bastian Rieck, and then appeared in 2021 in Frontiers in Medicine, a systematic review of the early prediction of sepsis in the ICU using machine learning. So we identified 22 papers after several quality filters. We identified 22 papers that were dealing with exactly this problem. 21 of them were developing a new algorithm or proposing a new algorithm, and one was proposing a new data set. Now, all of these 21 studies with proposing a new algorithm were retrospective studies that tried to predict sepsis on a data set that had been collected before. And 12 out of these 21 used the MIMIC database, an ICU database from Massachusetts. And 12 use the former international consensus definition sepsis 2, 9 use the current one, sepsis 3, and 1 uses sepsis labels annotated by medical experts. In this one study from Heidelberg by Chamoni et al. 2019. So you get a first idea of which kind of heterogeneity we are dealing with here. So these different studies even use their different definitions of sepsis, but it gets even more complicated. It's not only that in these 21 papers we have 3 different ways of defining sepsis, even going from one definition of sepsis to an implementation, to a software implementation of annotating a data set with this particular definition can lead to differences in different studies. So we have seen among these 21 papers cases where the authors of 2 papers stated that they are using the same definition of sepsis on the same data set, but the final number of sepsis cases that came out of that were different by 1 order of magnitude. So in one data set, like 15,000, and in the other, like 1 to 2,000. With the same definition on the same data set. And that points then at another problem, namely reproducibility. It's not as if you could then like download the software from these 2 papers and rerun it yourself on this database, which is often MIMIC. Often this code is not available. And this is also maybe a bit different between the bioinformatics community that we largely come from and the medical informatics community. So open source, open software is not as much valued. there, and I hope that's something that will change the more bioinformaticians come into medical informatics. So the code for this label extraction for the sepsis annotation is often not available. Then there's another problem of circularity that you at least have to be aware of when you do these kind of studies. I mentioned these time series before. You record blood pressure and so on, heart rate of a patient, respiratory rate over time, over hours, over days in the ICU. And then you try to predict sepsis. But sepsis is an event. So first of all, you have to annotate this time series with this event. So you have to find out, when does sepsis start in this time series? So based on these time series that you are observing, you're defining an onset time point of sepsis. And then you try with earlier observations in this time series to predict the occurrence of that event. But there is a danger in that you might be using the same observations for defining the sepsis event and at the same time using them for predicting the sepsis event. So there's a potential circularity that can occur here. So I'm not saying that this necessarily makes the prediction useless in every case, but you have to be aware of this problem. And of course, an even worse problem is if you take data from the future and use them to predict sepsis. This can easily happen. It sounds bad or funny, but it's not completely. Sometimes it's not easy to avoid this problem because these time series tend to be very incomplete. And then you start imputing the missing values. And there is a lot of potential for doing things wrong. So for instance, if you take the whole time series for imputing the missing values, then you may have this leakage from the future into the value that you are imputing. And then you are using information from the time at which a person already has sepsis to predict sepsis in the past. So be aware of these problems when you develop algorithms for these complications. And then there are a lot of details and a lot of knobs that you can turn in the evaluation of these models. I'll describe this in more detail on the following slides. It's to phrase it in one sentence, it's extremely hard to properly define controls for getting sepsis. So what is a person that does not get sepsis? There can be multiple answers to that. Now, among the 21 papers I described before, we saw that there are two main evaluation strategies, namely the conventional one, where you do everything retrospectively, and where you try to solve the problem that I described before, predicting whether sepsis will happen within the next X hours or not. And a second strategy that is rarer, but probably more realistic, namely to predict whether at a particular point in time, whether that person is about to enter a septic state or not. Let's have a closer look at these two different approaches. So first, the conventional one, as I call it here. So we have here at the top a case, so a person that does develop sepsis during the stay in the ICU. So that person, at some point during the stay in the ICU, fulfills the sepsis 3 criteria. And this is then the time point of sepsis onset, when that person fulfills all the sepsis criteria. And then what people do in the literature is from this time point, they go back Y hours into the past and pick a time window from the time series from the past. That's this shaded area, this feature window here shown on the upper left. Now, you want to now compare that feature window to a corresponding feature window in a control. But here the problem kicks in. If you want a corresponding feature window in a control, what is the onset time of sepsis in a control? Because a control doesn't develop sepsis. So what one can do now is to define a form of pseudo onset in a control patient, so in someone who doesn't develop sepsis. So for instance, there can be 3 strategies. So one is very simple. You pick a random time point in the time series of the control and say, this is my pseudo onset of sepsis, and then you define the feature window in the past relative to this random time point. Or you look at the absolute time at which sepsis occurred in the case. So let's say 24 hours after being admitted to the intensive care unit, that person developed sepsis. So you put the pseudo onset in the corresponding control also at 24 hours. So absolute matching. And then there's relative matching also. So if sepsis occurred after 50% of the stay of the case in ICU, you put it at 50% of the time of the ICU stay of the control as well. So these are 3 ways how it's done in the literature. Unfortunately, also in many papers, it's not entirely clear which of the 3 they are using. So it's clear that they are using one of them, but not which one. And the lack of code makes this not easier to understand which strategy has been used. And then the horizon evaluation is that you vary the starting time of that feature window. So you not only look at one time window, like 10 hours into the past, you look at 11, 12, 13, and so on. So like a whole range of time windows in the past, and you check how early can you predict that a sepsis event will occur in the future. And this is what is called, well, what we call a horizon evaluation. So you change the time horizon, the distance between your feature window and the onset of sepsis. This is the conventional way of doing that. That's the way how they do it in 90% of the papers in the literature. Of course, when you think about it, one day we want to use these early warning systems then in the clinic at bedside, and then doing it this way is very unrealistic in the sense that it's completely retrospective. So we have to first define or see whether sepsis has occurred here, and then we have to go back into the past several hours. So it's not really like a real-time or online way of predicting sepsis. It's a very retrospective way of predicting sepsis. So a more realistic one that is closer to the actual clinical deployment of such systems is that you make time point specific predictions. So at every time point, you predict whether that patient is in a septic state, yes or no. Now, the difficulty here is that, of course, you will not only label the sepsis onset time as then being in a septic state, but you will put a window around the sepsis onset time. So like a period during the stay in the ICU in which this patient was in a septic state. So you have to define a window around the sepsis onset. And in this window, the time points are annotated as 1. So as the patient being in a septic state. Outside that window, they are not in a septic state, so class label is 0. Controls are 0 everywhere. So you avoid this problem of defining the pseudo onset time in the controls. You trade it for this like problem of how big you should, or how large that window around the sepsis onset time should be. But often, like clinical researchers can give you some idea of how big that window should be. So that's the real-time evaluation, or pseudo real-time, one should probably say, of making one prediction at every time point. I've already mentioned like the relative benefits of these 2 strategies. So of course, in the first approach, we have a clear alignment. We have this feature window from the case and from the control. So we are ready to continue. I hope you can now follow me also online again. So I was talking about the lack of external validation. More than 85% of the studies we looked at do not use any kind of external validation. The big problem here is not only to get access to a second ICU data set. The big problem is that once you have like implemented an algorithm on one data set, annotated the sepsis 3 onset times, and then build an algorithm to predict these onset times, when you move to a second data set, one problem you may face is that not all the variables are available in that second data set to annotate sepsis, or not all variables are available that you are using in your predictor on the original data set. And even if they are available, they may have a different scale. They may not. So there's a lot of need to harmonize then these the data from different hospitals. So there are many pitfalls here, and that's why the vast majority of studies just does these evaluations on one data set, and then this, as a result, we have no idea of how robust they are across sites. And we have hardly any idea about the generalization abilities of these sepsis prediction and detection algorithms. And this motivated a large study of ours to harmonize the major public ICU datasets. This article is actually in press now. So that's a joint effort with the teams of Nikolai Mainshausen and Peter Bühlmann at ETH. And this is about to appear, this work in eClinical Medicine, probably in August. So in this paper, we do the following. We take the 4 major public ICU datasets, EICU and MIMIC from the US, HIRID, like a Swiss ICU dataset to which we also contributed, and the Amsterdam University Medical Center dataset, so one ICU dataset from the Netherlands. And we harmonized these 4 datasets in the sense that we identified matching variables. We mapped these variables onto each other and made sure that they are like standardized in the same way and that they have the same meaning. We made sure that artifacts are removed and units are harmonized. And this was actually a very big data curation effort of ours that also took multiple years. And at the end, we have now one big harmonized data set. We call it MC Sepsis for multi-center sepsis. And in this harmonized data set from these 4 locations, we have 136,000 ICU stays, 26,000 stays during which sepsis occurs, and 708 ICU patient years if you concatenate all of these time series. And for these patients, we have 59 time series variables. 50 of them are vital signs, and 9 are lab measurements. And we have 4 static variables. Gender, age, height, and weight are these 4 static variables. But now, this is the first of its kind, so like the first harmonized big public ICU data set that you can now use for method development, and in particular for external validation in method development. And it's not restricted to sepsis, so you can also use this for other medical complications that may arise during an ICU stay. Now, we use this data set to do a large-scale external validation of sepsis prediction using machine learning. We use the second strategy that I described before, this online or real-time strategy. So we defined a time window around sepsis onset, so 6 hours into the past, 6 hours before sepsis onset, and 24 hours into the future from sepsis onset onwards. This is the septic state that we define, and this is what we want to predict. And then we build various predictors from clinical early warning scores that are widely described in the clinical literature, to classic machine learning approaches or statistical approaches like logistic regression, to more modern deep learning architectures like self-attention based models. And what you can see here now is in every row one training data set. So AUMC is this Amsterdam data set, HIRID is the Swiss data set, MIMIC and EICU are the American data sets. And in the columns, we have the evaluation data sets. And the numbers here are areas under the ROC curve. So whether we can tell sepsis, one septic from a non-septic patient. And the area under the ROC curve is very high, as it has been reported also in the literature, on the diagonal, so in internal validation. When you train and when you test on the same data set, then the numbers are 0.8 or higher, so good to very good prediction accuracies. Now, off the diagonal, the predictions are also interesting, so they're actually also at least moderate to good to very good. So we have cases here where we train on one data set and still reach 81%, 83, 80, or 73% area under the ROC curve in this external validation when we move from one data set to another. So in particular, when we predict on the Amsterdam data set, we are often in the range of 73% or even more. And the worst numbers are 65%, so still significantly better than random. Now we were very pleased with that. So that's a first form of confirmation that to some degree you can successfully externally validate these sepsis prediction algorithms. They work across sites, even across countries. We even found one strategy that made these results better. This is what we call here the pooled N-1 approach. Here the idea is that if you want to predict on Amsterdam, you take the other 3 data sets. This is what we call, so the N-1 data sets. On each of the N-1 data sets, you train one predictor on each of them separately. So you get 3 predictors. And then for every time point in the test set from Amsterdam, you make a prediction with each of the 3 predictors that you have developed. And you take the one that gives the highest risk at that particular point in time. So you always take the prediction of the most pessimistic classifier at every point. This is what we call the pooled N-1 approach. So we only pool the predictions, by the way. We do not pool the data from the different hospitals. We just build one predictor per hospital and then pool the outputs of these predictors. And this works extremely well. So this is also a form of external validation. So here we reach between 72% and 84% area under the ROC curve in this form of external validation. And we do not even have to share the data between the different hospitals. So that's a very promising approach in our eyes. But one thing that I want to mention here is you also have to be careful about evaluating these predictions, because it's not only precision and recall that play a role here, or true positive rates and so on. There's also an element of time that you have to consider. So it's precision, recall, and earliness of the prediction that you have to consider. If you predict at the time point at which someone develops sepsis, then yes, the recall may be very high, precision may be very high, but earliness is very bad. So, and the plot here shows this in particular on the right, where we plot on the x-axis median earliness, and on the y-axis we have positive predictive values of precision at 80% recall. So when we identify 80% of those patients developing sepsis, like how high is our precision then? And for example, the red point up there is our deep learning model for this task. So we have around 55% precision and at 80% recall 4 hours prior to the sepsis event. And then when we move from internal to external validation, what we, for example, see is we can still achieve the same level of precision and recall, but the prediction is not as early anymore. So for instance, we then see that we can make a prediction like 1.5 hours before sepsis onset on the other data set with the same level of precision and recall, but not as early as in the internal validation. So that's another kind of dimension that you have to take into account in these studies, earliness. So to summarize this, we have created this harmonized public ICU data sets. The paper is now in press. The data and code are available soon, so we are preparing this for release. I'll tweet about this when this has happened, and then it's free to use for everyone. The idea is that you still have to apply for access, which is easy, to these public ICU data sets, and then we give you like all the code for producing the harmonized data set out of that. So because we are not the owners of these ICU data sets, so the official sites like providing these data sets, so you have to get them from there, and then our code will produce the harmonized data set out of that. In the internal validation, if we average above all the scenarios that we have studied, we reach an area under the ROC curve of 85%. And in external validation, we reach an area under the ROC curve of 76%. So that's a form of successful external validation of sepsis prediction that hasn't been achieved so far in the literature. Of course, it's all in silico. Of course, it's all retrospective, but still this result did not exist in the literature yet. And we found this interesting way of combining predictors that works empirically at least as well as using the best single dataset predictor. So when you compare these pooled predictions to the single best algorithm that you could get from any of the different datasets that we studied here, then this is usually favorable for the combination, these pooled combination of the predictors. And of course, in advance, you also don't know which the best single dataset predictor is. So this seems to be an easy and successful way of combining classifiers, at least on these datasets here. Good, so then I want to mention, to complete this first part of my talk, I want to mention other types of work that we have done in this domain here. So one item here is a collaboration with the teams of Gunnar Rätsch at ETH Zurich and Tobias Merz at Inselspital Bern, where we studied very related problems, just with a different phenotype, namely circulatory failure. And we predicted this in the intensive care unit using machine learning, using this high-rate data set that I mentioned earlier on. So what I've said here about sepsis also holds for other complications in the intensive care unit. Then with the Swiss Pediatric Sepsis Study and the Lurie Children's Hospital in Chicago, we did, and this was actually work at last year's ISMB, we predicted the recovery from multiple organ dysfunction in children that developed sepsis. And this is, from today's perspective, a very interesting study for us, because here we followed a different way of doing external validation. So I've just described this big effort of ours to create this harmonized data set. What we did here in this study is we developed the prediction algorithm for this recovery from multiple organ dysfunction on the Swiss data. And then we sent the code to Chicago, and our collaborators in Chicago ran the code on their data. So that's a completely different way of doing this external validation. And so we never touched the Chicago data in this project. We just shared the code. And this, of course, now points at like one big debate is maybe too strong, but two strategies that are being pursued here in the community. One is centralizing the data, harmonizing the data. The other is a more federated approach, where you keep the data in different locations and you try to do the learning without combining the data. So both of them have huge challenges and huge pitfalls. So in the federated learning, for example, you make very strong assumptions about the uniformity and the standardization of the data. So you must really trust that each of the sites from which you use the data for learning has brought the data into the same format. And centralizing the data has other huge issues, for instance, legal issues. And I know what I'm talking about because I did this I was heavily involved in this for Switzerland. So when you harmonize the data and you centralize them, then you need legal agreements between all the participating sites that they are willing to transfer their data and that they are allowed to transfer their data. And this is years of legal work. So that will delay your project, for example. So that then again speaks for the federated approach. But as I said, so in the federated approach, you often make very strong assumptions about the state of the data that you are working with. And this is then often only the case for a very small subset of the data. So we are still struggling with both of these approaches currently in the field. And this will continue to be one research challenge, like to find a very good solution for this issue. Yeah, so I mentioned this Swiss effort that I was involved in. So this is the personalized Swiss sepsis study. We harmonized since 2017 intensive care unit records from all Swiss university hospitals. This was co-coordinated by Adrian Egli, who was back then in Basel in the university hospital, and myself, I was back then at ETH Zurich. And as of 2022, we had harmonized 18,000 health records collected in the Swiss university hospitals. As you heard in the introduction, I recently moved to Munich to head a new department at the Max Planck Institute for Biochemistry. So now Catherine Jutzler from ETH and Adrian Ekli are continuing this project. It has been upgraded to a national data stream for intensive care research. So has hopefully a longer and promising future ahead of it. And we are still, after harmonizing this data, we are now in the process of building sepsis prediction algorithms on this data from Switzerland. So this is what I will do as in terms of completing my contribution to this project. So to summarize this first part, I hope I've convinced you that comparability, reproducibility, and robustness are key issues in sepsis prediction. And in fact, not only in sepsis prediction, in all of machine learning in medicine in general. Then the harmonization of ICU data from multiple sources is a huge challenge, actually, even if you do federated learning. To make sure that data from different places is in the same format is a gigantic effort in this domain. A legitimate question to ask when you talk about sepsis prediction from clinical data is, what about omics data? Can we collect omics profiles for these patients and make these predictions better? So there are plans to do this as part of the Swiss program. And then, of course, one of the big next steps is to go away from this retrospective validation to a prospective clinical validation, that we really put an alarm system at the bedside, and that goes off when the computer thinks that, or when the algorithm thinks that this person will develop or might develop sepsis within the next X hours. And that we then study, does this help the doctors? Do we reduce mortality by having such an early warning system? Do we shorten the length of the stay in the ICU and other objective criteria? And sepsis, of course, can not only occur in the ICU. There may also be important clinical variables that are collected before you enter the ICU. So integration of pre-ICU data is one challenge. And sepsis is also not over when you have survived like the infection and when you've left the hospital. So they are often, like maybe similar to long COVID, there are long-term consequences of sepsis. You may get sepsis again and things like this. So studying these long-term effects of sepsis is another line of work that is very promising. And as I mentioned before, many of these approaches and insights apply to other clinical prediction tasks. So this is certainly a very rich field that is worth further studying in the future. It's a highly exciting topic for machine learning in medicine. So now with 20 minutes left, including the questions, I'll give you a short tour of the second part that I wanted to talk about, namely our attempts to do antimicrobial resistance prediction. You can also think of antimicrobial resistance as a form of complication that could arise during the stay in the hospital and that you want to avoid if possible. It's, as sepsis, a global health threat because antimicrobial resistant pathogens increase morbidity, mortality, and healthcare costs. And ideally, you would rapidly treat a patient with effective antimicrobials to improve the outcomes for this patient and to have optimal stewardship in terms of antibiotic use. And this is such a big global health threat that even the World Health Organization is publishing strategy papers on how to deal with this challenge of antimicrobial resistances. Now, in fact, in a way, this project was a spin-off from our sepsis work because it's a collaboration between my lab and that of Adrian Ekli, who co-coordinated this sepsis network with me. So they asked us as the machine learners, can maybe AI help to speed up and optimize the antimicrobial treatment? Can AI help to identify resistances early on during the stay in the hospital? And they had a lot of data in the microbiology lab in Basel that we could look at for studying this problem. But to understand how exactly we use this data for making predictions, I first have to describe the infection treatment workflow in a hospital like the University Hospital Basel in Switzerland. So when you have an infection in the hospital, then there is a sample collection usually, and then this sample is grown on a plate for 12 to 24 hours. And then you do a Multitoph measurement, so a mass spectrum is obtained from this sample. So that's like a proteomic fingerprint of that sample. So like a fingerprint of protein fragments from this sample. And then this mass spectrum is used to identify, in Basel, is used to identify the species of the pathogen. So that's what is routinely being done after 12 to 24 hours. They can tell in most cases, the species of the pathogen that has infected you. And now, in the second step, and that's shown here on the right, they now put that pathogen on different plates and apply antimicrobials to these plates and check whether the pathogen, they experimentally check whether the pathogen is resistant to these antimicrobials. And this takes between 24 and 72 hours. And then they experimentally know which resistance phenotypes this particular sample, this particular pathogen has. Now, what we are trying to do with machine learning is to speed up this process and to use the Multitoph measurement, so the mass spectrum that we get after 12 to 24 hours, to predict whether this pathogen has resistances or not. And then to provide this information to the doctor after 12 to 24 hours rather than waiting for another 24 to 72 hours. So this is the question, the hypothesis, or the goal that we had here in mind and that we studied in this collaboration. I mentioned this mass spectrum before, so it's a standard technique for species identification in clinics. It gives you an overview of the protein composition of that sample, and they are, as mentioned before, highly characteristic for microbial species. So there, it's really clinical routine to use this this type of mass spectrum for species identification. And now this work led to this publication with the ECCB lab, Weiss et al. In Nature Medicine 2022. What we did in this paper was, first of all, again, we created a huge data set. So we got mass spectra and corresponding resistance phenotypes from all big hospitals in northwestern Switzerland and from all private laboratories, or from the big private laboratories in northwestern Switzerland. So we had more than, in combination, we had more than 300,000 mass spectra, and we had more than 700,000 corresponding resistance phenotypes from these 4 different sites here. And we called this, the combination of these, the database of resistance information on antimicrobials and Multitoph mass spectra, short TREAMS. And TREAMS A, B, C, D are the 4 sites in northwestern Switzerland where we have this data. So you can see here the University Hospital Basel is the biggest out of these, so it's bigger than the other ones combined, in fact. And then we collected this data, we pre-processed it, we pre-processed the spectra, which is also like a very interesting and intense data curation effort. And then in the green panel here on the right, we then really did machine learning. So given a particular pathogen and antimicrobial, we predicted whether there's a resistance, yes or no. And this we did for various types of classifiers, from logistic regression, here referred to as LR, to tree-based methods like light GBM, and to neural networks like the MLP, the multi-layer perceptron here. And we observed that we could tell resistant from sensitive pathogens with good success. So here on these 3 species antibiotic pairs here that are particularly important, according to the World Health Organization, we reach between 67 and 80% area under the under the ROC curve in telling resistant from sensitive. And of course, like experts in this domain may now say, oh, but the mass spectrum is not fine-grained enough to really pick up the resistance mechanisms here that allow you to identify resistances. This is correct, in fact. The prediction is often indirect. It's a non-causal prediction in the sense that we are picking up properties of these pathogens that are correlated with resistance, but not causal for resistance. For instance, in this prediction of resistance for ceftriaxone treatment in E. coli, we pick up sequence positions that are typical for a particular clonal lineage of E. coli that has multiple resistances, but none of these is actually connected to a particular resistance. It's just typical sequence variants of that particular strain that happens to have other resistance resistances, and then to share these. So we are picking up sequence properties that are correlated with resistance, but not causal for resistance in several of these prediction tasks for species and antimicrobials. Now come again to the validation. There are, of course, there's again here like an internal and external validation task. So to how well are we doing within one hospital? This you can see here on the diagonal. So this works decently well for E. coli and ceftriaxone. It gets harder, although it varies a lot when you move from one laboratory to another one. So then it starts varying a lot. In this particular example, it's still better than random for all of these external validations, but there are also in this huge data set other examples. So for Klebsiella and ceftriaxone, here we have some combinations where the results are actually random, where we cannot transfer this successfully to another site. Is it a question or a reminder?
For background,
yeah.
What are typical numbers with baseline, with state-of-the-art methods that you're competing with, so that we can put it in context?
So this is so the baseline, the statistical baselines we implemented ourselves. So what the actual baseline is in reality is the experimental validation, and they get it typically right? So, but they take much longer. So it's again like a earliness correctness trade-off. Yeah. So we can get an uncertain answer much faster. They can get a certain experimentally determined answer within 1 to 3 days. And we can do a prediction that could be wrong immediately without time delay. And this is the trade-off that you have to look at and like then analyze whether the trade-off is worth. So what I want to say with this plot, these two plots here, is that there are examples where the validation works rather well. There are examples where the validation does not work at all. This seems to be a species antimicrobial specific, and this deserves further exploration, why this is, how this can be improved, and so on. Another level of validation here is temporal validation. So as we are often only using like correlations for predicting resistance here, so our system might not work anymore if new like species or new resistances are entering a certain region like northwestern Switzerland. So over time our predictions may get worse due to that. Another reason may be that the Multitopf machines are being recalibrated once in a while, and you can really see that this has an effect on the mass spectra, and then also the quality of our predictions may deteriorate. So we examined this systematically here in this plot. So this plot here goes from 2016 to mid 2018 on the right, and the test set was end of 2018. So the predictions at the right end of these plots are close. So this is no, I have to correct myself. So here we see here on the x-axis when the training data set was collected, and that was between 2016 and 2018, as I said before. And the test set was end of 2018. So the predictions at the very left, were trained on data that was very far in time from the test set. And the predictions on the right were trained on observations that were rather close in time to the test set. And you can see here that there's a trend that the predictions get better the closer the distance between the training, the time of data that was used for training and the time of the data that was used for testing. So the closer you get, the better these predictions get. So there's a temporal component in the validation as well. This, in my opinion, says that you have to retrain the classifier once in a while to stay up to date and to keep a high level of prediction quality. In fact, due to the particularities of this application here, you could do that because as I said before, the hospital is routinely collecting these mass spectra for species identification, and they are of course also routinely determining resistance phenotypes experimentally. So there's constantly new data being collected that you could use for training and for retraining your model over time. And that also makes this problem with spatial validation sometimes working and sometimes not working smaller, because you could really in one site, in one hospital, in one laboratory, have a system that constantly retrains itself and uses local data from that laboratory to update its predictor. So it's like a machine learning problem where you are constantly collecting new training data sets at each site, and that diminishes the importance of this validation across sites a lot, in my opinion. And then we had a clinical researcher look at our predictions and whether they would have changed the treatment of patients in the University Hospital Basel. For 63 patients, we had enough data to study this problem. And then we gave to this infectious disease specialist our prediction and the electronic health record. And we then checked whether our prediction would have changed the treatment of the patient if it had been available at the time that the species identification was made. So before doing this experimental determination of resistance phenotypes. In 54 out of 63 patients, there would have been no change to the suggested antimicrobial treatment. In the other 9, there would have been 7 times a de-escalation of antibiotic therapy, where it was previously continued. Previously is what the doctors did in reality. 1 continuation of therapy, where it was previously escalated. 1 escalation of antibiotic therapy, where it was previously continued. Only this very latter case, the escalation of the antibiotic therapy that was suggested by our algorithm, was wrong. In the other 8 of 9 cases, what our algorithm proposed was actually beneficial to the patient. So we have 9 out of 63 cases in this retrospective clinical case study where our algorithm led to a change in treatment, and 8 out of 9 times this was beneficial to the patient. And now the next big step is now for us, but we are planning that, to do this in a prospective clinical study as well. I also observed when going through the data that there's a very interesting phenomenon here. So it's clear that the algorithm and the doctor make mistakes, actually. And it seems that the combination of both is actually the best strategy. So when looking at these results, I noticed that sometimes the algorithm is compensating for the doctor's false assessment. Sometimes the doctor is compensating for the algorithm's false assessment. So maybe that's also like a model for the future, that the human doctor and the machine support each other, and that the combination gives better results than each of them on its own. To conclude, this was the first large-scale study to analyze the clinical potential of MALDI-TOF mass spectra-based antimicrobial resistance prediction. There had been approaches in literature before for doing that, but not at this scale that we had here, not with hundreds of thousands of mass spectra and hundreds of thousands of resistance phenotypes and hundreds of pathogens and dozens of antimicrobials, as in this work here. Transferability across space, across time remains a challenge. The data set is already available. It's on Triad. So it's available. You can use it for your own work, and also the code that we used for doing these analysis is available on our GitHub repository. So with this, I'm at the end of my talk. I would like to thank my lab members. Almost all of this work happened at ETH, so I'm also thanking ETH for that, and our other sponsors. It now continues at the Max Planck Society. This is one of the last Facebooks of the team at ETH. I'm now regrowing the department at the Max Planck Institute for Biochemistry in Munich, and one goal is there to do the things that we did in Switzerland now and to continue them in Munich, and to do a mild form of advertisement. So I'm also hiring PhD students and postdocs for that at the moment. So for strengthening our new efforts in medical informatics. So if you're interested, let me know. And with that, I thank you for having me here today, and I'm happy to take questions.
Thank you very much for this interesting talk.
Can you please go back to the slide where you showed the preprint or the sepsis paper, please, so I can take a picture? Thank you.
Yeah. It's an e-clinical medicine. It will appear. I have to go here. The title changed slightly between archive and the publication. Yeah, please. Okay. So Joaquin is the master of the.
So a question on the temporal validation that you were showing.
Yeah.
Do you think that this is reflective then of real-time resistance mechanisms being captured in your model and kind of improving upon that?
I think partially yes, but there's also technical variation that's being reflected here. So as I said, I jumped over it. So also the machine being recalibrated may make a difference. In fact, even the person handling the machine may make a difference. So so there are technical confounders here also. So not only biological variation is the source of this. That speaks for retraining. Yes, please.
Yes. So thank you very much for the excellent talk. So are you planning, which kind of novel types of data are you maybe planning to bring in the future? Because, using the MALDI-TOF is one thing, and obviously you're bound by the existing constraints of typical hospitals. But say, if you got a choice, if you could make a wish, which kind of additional biological data you would collect, what would it be in both cases?
So probably you could further improve this antimicrobial resistance prediction if you used covariates that describe the patient from which this sample was taken. So that's actually very likely that you can further improve it. It will hinder this type of research a bit because then you need ethics approval. At the moment, you don't, because it's all just pathogen data. It's all properties of the pathogens. There's no patient privacy here. So that's why we can put this huge data set online. So there's no patient data. So we want to do that, but it will make the data acquisition, ethics approval, and so on much more difficult if we do that. And but we might gain another few percent in prediction accuracy when doing that. Yeah.
Thanks for your talk. I was wondering whether the vital signs and the labs and things that are involved, whether those take into account differences in those ranges based on pre-existing conditions, such as, for example, if a patient has sickle cell disease, those ranges, what's normal for them would be different in many cases. Whether pre-existing conditions are taken into account. And for example, someone with sickle cell disease, if perhaps they're in the ICU and you don't know that they have this, perhaps they're in such a state that you don't know, they can't tell you. Is there something, does that involve, any of those vital signs or labs? Do they involve checking for something like that?
So this is a very, very relevant point. It is probably available in some of these data sets, but not in all of them. So when we harmonize them, we have to somehow restrict ourselves to the largest common denominator here. And so these are now very basic vital signs and very basic lab tests that we are considering here. So you're pointing at a very important issue. There may be very important like variables like health history, and that is available in one hospital but not in another. And then you can build a very good predictor in one hospital because you have this health information there, but not in the other one. So the one, I think this is not really solvable with the data that is currently available. I mean, the goal here should be that we have a very high standard of which kind of information is recorded about a patient, and that this standard becomes as global as possible. I think that's what we have to aim for. Yeah. Yes. Sometimes I'm not, so I can't guarantee it for the particular example that you mentioned, but sometimes the machine learning can still pick it up from the vital signs. So there are some pre-existing conditions. So it may be reflected in the vital signs. Yes. Even if you don't have the variable stored explicitly in your database. Okay.
Thank you for the nice talk. So when you go back to the AMR dataset, then like because of the clinical procedures, there must be like really highly imbalanced on the dataset. Like for example, specific species, they do some screenings, but on species, like specific species, they don't do screening. Then like I'm wondering like how did you handle the data imbalance?
Yeah, so you're very right. So the datasets are very imbalanced. In fact, if we tried to turn this here into a diagnostic test, then we would have to look at what they call major errors and very major errors in microbiology, that we miss resistances, that we incorrectly predict resistance. And so the level of our predictions is not at that point that we could like register this as a diagnostic test in that sense. So we can support the doctor in a retrospective study successfully to getting this to the level of a diagnostic test that then also accounts for this imbalance and so on. This is yet another step that has to be taken in the future. Yeah.
One quick question, please.
Thank you very much for the nice talk. I'm interested to find out why in both use cases you didn't choose to pool the data sets, but rather train the separate models on each data set and then compare the performance. As in machine learning, the more data you have, the better your model. So as you have several data sets, I was wondering why you didn't leverage all of them to train models.
In fact, we did that, but I did not focus on it in my talk today. I have a backup slide for one of these data sets. So here in this slide here, we tried out what's the best strategy for getting good predictions on TREAMS B, so one of the smaller data sets. And what we observed there is good strategy is to use a big data set like TREAMS A, that was the biggest one from Basel, and to combine it with some data from TREAMS B. So this is here the third results column here. So there we reach across these different species, antimicrobial combinations, the highest areas under the precision recall curve. If you have a lot of data, general data, and some specific data from that site. So this is a question that is very important to us, but I did not focus on it today.
Thank you.